Hello, this is Polymorphic Reconcilers, Advanced DuckTyping in Kubernetes. I'm Scott Nichols. I work on Knative eventing, focused on sources, and I work at VMware. And this is Matt.
Hi, I'm Matt. I also work at VMware, and I am focused on leading Knative serving. A little bit of feedback. All right, a little bit of background before we jump into the main event today. So custom resource definitions, AKA CRDs, AKA the new hotness, are leading to an interesting change in the Kubernetes type system. We've gone from a world where we have a relatively small fixed number of types if we want to reason about compute things like deployments, daemon sets, jobs, stateful sets, types of compute, to a world where any schmo off the street, like us, can start to build higher level compute abstractions. So for instance, in Knative serving, we have this service and configuration resources, a bunch of different things in the FAST landscape, such as Kima and OpenFAST and kubeless have function CRDs, and this list goes on and on and on and on. And so we have this now new, unbounded, ever-expanding space of compute abstractions. So the question we started to ask ourselves is, as controller writers, how can we, if I'm going to reason about not just one particular thing, but the class of compute resources, how do I write controllers that can deal with this entire class of unbounded app resources? So option A, bake it in, right? So as these things come up, you just play whack-a-mole and you build it in, and this gets really tedious. So we started looking for an option B. Welcome to the Untitled Duck presentation. This is our mascot, Vile. All right, so while we put on our wonderful hoodies, yeah, Vile is going to be handing out the DuckTyping stickers in the back at the end. That's this wonderful logo. Folks in Knative, I created an emoji this morning. All right, so we gave a talk on DuckTyping in Barcelona. We'll put this link up at the end. You can see Scott. I got to wear the costume then. We'll put this link up so that you can see it with a wall of links at the end. But we're going to quickly recap what DuckTyping is and try and cover largely new content and demos so that if you saw that talk, you don't fall asleep. So without further ado, the Untitled Duck presentation. Well, I'm not keeping up. Okay, the first thing we're going to do on our to-do list is quick recap. So DuckTyping. So DuckTyping is, here we have three different objects, right, that have this common theme. Each of these has a foo.bar property, and if I want to reason about this collection of different resources and reason about that foo.bar property, DuckTyping allows us to define a partial schema that allows us to extract that information from different resources within this class. All right, so how does this relate to Kubernetes? So Kubernetes actually has a number of instances where the idea of a partial schema is very relevant. So every single Kubernetes resource embeds this type meta thing, this API version in kind. It also embeds object meta, this metadata thing that everyone is, every senior YAML engineer in the room is very, very aware of. So the apps resources also define an interesting duck type, which is they all embed a pod spec in the exact same way. Spec.template is this thing, core v1 pod template spec. So they all embed this same shape, and one of the things we showed in our previous talk is by leveraging this, we can actually take arbitrary resources that do this, and we can extract that information. We can leverage patching to actually mutate those without knowing the full schema of these objects. So, cross that off our to-do list. Next, we are going to talk about the concept of bindings. So, what is a binding? So the way I think about bindings is largely in terms of runtime contracts. So whenever I run an application, it runs in an environment. That environment has certain facilities that may be provided by the system. An example of this would be the Kubernetes service account token and endpoint that allow you to sort of extract that information and talk to the API server as if it were magic when you're running on a cluster. A lot of cloud vendors provide HTTP metadata endpoints on the network that you can talk to determine identity information and retrieve access tokens. There's also facilities like, if I write to var log, it may, my logs may magically appear in some sort of durable logging system. So, as an application developer, this idea of binding is really powerful because it allows us to start extending that runtime contract in interesting ways. So, the application developer can just assume certain properties like those and build their apps with that assumption, and that can be late bound into it by the environment. So, what are some things we might want to bind in, right? Secrets, config maps, sidecars. So one of the things we're going to show now is a proposed direction that builds on this that we might want to use to implement Knative event sources. So we could call this POC the sync binding. So there's a couple key elements of the sync binding. There's the target. This is the Kubernetes resource whose runtime contract we want to extend. In this case, we want to inject a simple environment variable into that binding target that says, hey, send events here. There's also the event sync. This is the Kubernetes resource that we want to send events to. And then the sync binding basically is responsible for extracting the information about how to send stuff to the event sync and projecting that into the binding target. Easy, right? So the question is, how do I stick a sync environment variable into all of these? And how do we take all of the things we might want to deliver events to and extract the address to send those things there, the value to put in this sync environment variable? Option A, we bake it in, right? And we, okay, gets tedious. Option B is our duck types. So for the target and the sync, we're going to use two different duck types. The first is that class that we talked about a little bit earlier. Kubernetes application resources fit this mold, and a few other resources like the Knative resources do as well. Basically, if you embed a pod spec at spec template, it forms a class we've started to refer to as pod specable. For the sync, this is OG duck typing. This is what we call our addressable duck type, and it is what the contract that has allowed us to effectively have serving and eventing be loosely coupled, but work really well together. So the next question is, how do I write controllers that can effectively operate in this model? First part is your traditional controller. So it reconciles sync binding resources, and if I want to be able to have the sync change over time, it can basically extract that information, and it's continuously reconciling where the sync says you should send events with a sync environment variable being present in the target. However, there's two interesting problems that just doing this as a traditional controller doesn't work for. So one is immutable resources like a Kubernetes job. Kubernetes jobs are pod specable, but as soon as they're committed to etcd, you can't patch it with where to send events. Another interesting case is when, say, take a Kubernetes deployment. We created a Kubernetes deployment when we stamp out Knative revisions. That's owned by another controller. If you start patching the deployment that we own, we're going to patch it back, and we're going to fight all day, and it won't end well. So to address this, we also run a mutating webhook. So this mutating webhook addresses both of these problems. Effectively, for immutable resources, it allows us to perform the binding before the resource hits etcd. And for cases like a controlled deployment, basically by doing this in the mutating webhook, it ends up looking like really fancy server-side defaulting, and so well-written controllers already have to deal with the possibility that the create or update operation has more values filled in, and to deal with that. So that's the high-level overview of the binding we're going to walk through next. Let's see a demo of it. Okay, so I'm going to open up a whole bunch of examples. Okay, and the first thing we're going to do is I am going to launch a simple container called debug, and it is an Ubuntu container that I've just installed curl on, and we are going to exec into it. And I just want to show you that if I echo sync, nothing, right? So our base runtime contract doesn't have an environment variable named sync. So now if I exit the container, we have a simple sync binding defined here, where the deployment named debug, which is what we just created, is going to have the address of a service named sockeye basically projected into it. So if we, let's see, let's kube control apply this. Now, sockeye is a tool written by this fine gentleman. I'll pull it up in just a second, because multitasking is hard. All right, so if I exec into this now and echo sync, we'll see, hey, the new pod has this sync environment variable defined, and it has the address of where to send events. So the next thing we're going to do is we're going to pull up sockeye.default.ducktyping.io, and we are going to grab this curl. So as soon as we curl this, basically the way Sockeye works is it opens a WebSocket to my browser, and as soon as, as soon as I curl this event, joke's on you, I'm a deployment shows up here. So by curling the sync environment variable in that container where we've extended the runtime contract, we know where to send events. Okay, so for the next example, this shows us doing it with a mutable resource like a deployment. What about an immutable resource where after it's created, we can't change it, right? So I am going to exit the container, control apply -f example job. All right, no more bananas. As soon as this job runs, right, we see hello from a job, right? And the curl, it ran the same container that is running in my deployment, except we set the entry point to curl it and send this event. So now we've shown mutable thing, immutable thing. Let's show what this looks like with a Knative service, which is a CRD that's defined, and we have no baked-in knowledge of this in Sockeye or the sync binding or anything like that, right? So if, and here I have a simple proxy image. All it does is it listens on 8080, and every time it gets an event, it sends it to what the sync environment variable says to send it to. So if I apply this, control apply, and then we are going to curl the proxy and send in an event that says, I went through a Knative service. So let's see. As soon as I hit send here, boom, I went through a Knative service. So we've shown mutable, we've shown immutable, we've shown user-defined types. So now we're going to get kind of fancy. So fancy. OK, so this goes back one example to the job, except this version of the job, instead of sending it to Sockeye directly, is going to send it to that proxy we just created, which is also a service, so also addressable. And this shows that with bindings, really with the same job definition, the binding can actually completely change where that application is sending events. So if we apply example fancy, as soon as we come over here, let's see. Boom, hello from a job through a service. Okay, so for the last demo, I'm going to apply it first, and you'll see why in a second, because this takes a second. Okay, so now we're going to get super fancy. Now, we're going to do that same thing we just did, except we're going to have those jobs stamped out by a cron. The cron job every minute is going to create a job that does the curl. It's going to label those jobs with app curl cron. And in place of a direct reference, we're now selecting those jobs with a selector. So every job that's labeled with app curl cron is going to get sync bound in as it's created. It's going to run. It's going to send an event to Sakai. Or sorry, to proxy, which is going to send it to Sakai. So you can see here that the cron has run, curl a lot. And if we switch over to here, we now have hello from a cron job via selector through a Knative service. Okay, so just to recap, right? Visualize it all, right? So we created a mutable thing, we created an immutable thing, we created a user-defined type thing, then we used the immutable thing to send things through the service. Then we created a cron job that stamped out jobs that sent things through the proxy onto the service. So now I'm going to hand things over to Scott to wrap up our to-do list.
Thanks, Matt. Okay, so now we're going to talk about dynamic type controllers. So Matt just showed an example of there's a reconciler that's reconciling a concrete type in Kubernetes. In that case, it was a sync binding, and inside it had two known duck types that the controller could treat that as an interface because the contract of the sync binding was that these two places, the resource we're pointing to, adheres to this other kind that we know about. That's great. That's very useful. But what about the case where you have a reconciler that you would like to implement that reconciles on the duck type directly? You can't do this in Kubernetes because all of the clients and all of the caches and all of the reconciler queues are strongly typed with a kind because you have to set the watch up. Kubernetes just doesn't let you ask for anything that matches things like this. So we have option A. We could do manual config, like a config map. So we could, every time we install a new CRD, we could update the config map, and we could have some sort of watcher watching config map changes and stamping out copies of a reconciler injected with GVRs or GVKs, and the logic doesn't have to change, but how we load stuff changes a little bit. This works until someone deletes that CRD, and then now we have a reconciler reconciling on an unknown type in Kubernetes, and your controller just starts throwing errors. I bet you that whoever deleted the CRD won't update this config map. So that's a problem. But we have more options. The thing that happened was that someone came to the cluster and deleted the custom resource definition. So we could use that as a place to store metadata. So in Knative, we've been labeling our custom resources with the duck type that they implement. So in this case, serving implements addressable, like Matt was just showing. There's also an object called a broker. It's also addressable. So we can label it that the duck type is addressable. And now we get to write a CRD, another reconciler that reconciles custom resource definitions, but this time it filters based on that label that we've defined. And then it can update that map internally, just in memory, and stamp out reconcilers based on types that it observes in the system. And this is awesome because if one goes away, we can clean up by ourselves. Did it. Okay, so now we're going to demo what a dynamic type controller could do. But first, I have to give you a little bit of context. We're going to leverage Knative eventing to do this. So we have, there's a concept called the broker. It's basically an event mesh. That's the events go in. They come across the broker, and you can create a trigger that if the trigger matches the filters that you specified, it takes the event, a copy of the event, and delivers it to a consumer. with one little gotcha, you can respond with a new event, and it's just like it got ingressed back into the broker. So another trigger could filter on that new event, so you can get kind of these cyclical loops. So we've already shown how we can solve the random deployment into broker. But what about, we have this problem where we want to make a function, and we want to make a trigger, but if we make a copy of the function, or the service, or the whatever, you need to manage the other pair, the trigger as well. So this becomes a little bit of a little cumbersome because you'll delete the service and you'll still have the trigger, or you'll accidentally delete the trigger and the service is then a dangling node. So started thinking about this, and well, we could apply this duck typing concept. We could have a controller reconciling all addressable types because we have that metadata. And then I can stamp out copies of the reconciler that implements the Autotrigger controller. And so in this case, it's service and routes. That reconciler sees a new service, and it sees some special annotations and labels. It uses that metadata to create a trigger for the broker. And now we can automatically connect, and we don't have to think about that. Ooh, sorry. Okay, so we're going to demo this. I am a VI user. Matt uses Emacs. So Matt's going to type. So Matt's going to apply a cluster configuration very similar to what we just showed. There's going to be a random number generator that's sync bound into the broker, and it's going to make random numbers every second between 1 and 100. So very similar to the demo that we showed earlier. And then there's a function that we call classifier. The logic is just it looks at the number and it says if it's odd, it labels it odd. If it's even, it labels it even. So this is filtered on type, and then we're going to send those new classified objects to just a copy of sockeye. But this time we're going to use a Cloud Event extension with the custom label that we are reintroducing. So it's a new event, it goes back into the broker, and the new trigger picks it up. So if we go and open up an odd or even sockeye, and we start seeing odd and even events. Awesome. No. Okay. Back to the presentation.
Done.
Oh, hey Matt.
What's that?
There's a bonus task.
Oh, visualize duck-typed relationships.
So we got to thinking, and you don't just have to write reconcilers that run in your control plane for these duck types. The duck types that we've been playing with help you understand how the relationships between objects that we've been creating. So we're going to show you a graph program.
Wow, that one on top looks familiar, Scott.
So above is the graphical representation of the demo previously, but the graph program doesn't understand sync bindings at all. It only understands, it can find objects that are installed labeled with that source label. They can also see things that are addressable, and we can infer connections based on this because we know the shape. So there's that graph, all right? So you see the normal one straight to sockeye, and then the super fancy one that goes into the proxy and goes into sockeye. And then we see basically the same setup we saw. So we have a generator, goes into the ingress of the broker, and then each trigger. But the interesting thing is that because we are writing a controller for the Autotrigger, the consuming service that is asking for a filter for triggers, we know who it is. So we can set its owner reference, and so we can get automatic garbage collection. All right, so this is, it's actually hosted in a Knative service, running in a cluster. It's dynamic, so every time we load the page, it'll requery. So if we reload real quick, sweet. So Graph actually uses 3 duck types that we have in Knative, and one of them is it understands the general shape of what we use for status. So we can see arbitrary ready conditions, and I can look at that and understand how to color the graph to give you hints about what's going on. So it went ready. So we added a new function that does prime classification, and if you would guess, it then filters events that come through, it labels things that are prime, and it shows it up on the sockeye service that's prime. So, yeah.
All right.
We did it. Questions?
To do as well, questions. And we're going to put up a wall of links.
Thank you so much. It's an open mic. Hands up over there. And yes, I'm a runner.
The first question is, we have produced, we've produced these stickers, so yeah, so the duck has them in the back. Question?
This looks really cool. I'm actually curious how you're determining shapes. Are you actually looking at like the CRD specification and like the API spec, or are you doing something at the Go layer? Like, where is that happening?
Good question. So right now we're not doing anything based on the Open API schema, although that's an interesting thing we've thought about. We actually don't publish the Open API spec in the Knative resources yet, but
we only do partial schema from the parent down. So
yeah,
so it needs that one leaf and all the way down.
Yeah,
so we can do merging.
So for the second half, we basically leverage labeling, right? So if CRDs that are labeled saying I am addressable or I am a source or any of a variety of different duck types, you can basically reason about those resources with the expectation that they implement that shape. They have that common partial schema. For the SIG bindings, basically, it's somewhat on the user. There isn't really a great way to validate this right now, or at least we haven't come up with one. If you have ideas, let us know. The schema one is definitely an interesting one that we haven't fully explored. Yeah, so if you reference a pod specable thing in the target of the sync binding, I mean, ultimately, if we try and start patching that, or if it goes through the mutating webhook and we try and apply a patch that we can't apply, it'll actually get rejected, assuming there's good validation after the mutating webhook runs. So hopefully that answers the question in both contexts. If not, happy to keep discussing. Great.
So when you did the cron job, the cron job wasn't what was actually injected there. It was the job that it created through the mutating webhook. What if the thing that you wanted to actually inject was the cron job, which doesn't have a template spec at the top, but does 2 levels down? Have you thought about where things, they have the type, but it's just not at the same path?
Yeah, so you caught us. No, yeah, cron job actually is not pod specable. It has some extra layers in there. Yeah, so if you wanted to do it with a cron job, it would either have to be, you would either have to start teaching it about multiple shapes and a way to disambiguate when to use one shape or when to use another shape, yeah, I mean that's mainly it, right? So one of the things that we were sort of fiddling around with and kind of wanted when we sort of figured out that we could do this the way we're doing it with DuckTyping was the idea of custom sub-resources. So Kubernetes has, for instance, the status sub-resource, the scale sub-resource, but for CRDs, there's really only Those two, I think. There may be a third that I'm blanking on, but you certainly can't create your own. So if you could effectively say, so when I'm defining my scale sub-resource, for instance, I tell Kubernetes where to extract the various properties of the scale sub-resource, so the selector, the replica count, the desired and actual replica count. But if we could do that effectively for where in my object is the pod spec, that would be pretty cool, and we could potentially do something more powerful. But then, again, that's sort of like having some higher level information that we could use to disambiguate and guide how we're doing it for various types. So yeah.
Like all things, we're starting small, we're building on
Yeah.
things we know, and so now we have this, if the shape is exactly what we expect, but there's other noise around it, we can deal with that. We could probably work, now that we have this, we can also add, by the way, you can look in a different path. It seems reasonable. All the way in the back.
You did this on
All right.
purpose.
After this, it's your turn,
Somewhere
Ben.
here.
I'm looking at you.
Thanks for the run. So any reason why you chose shapes for matching and not some kind of expression language such as XPath?
So we're trying to solve the problem is for eventing specifically, and the reason the first DuckTyping talk happened, we have all these consumers, those consuming functions, but that consuming function can be any other thing. So custom resources, as long as they expose how to talk to them, we can wire things together without actually understanding. So we've kind of started and focused on it must be this path, and also there's a bunch of machinery inside of Kubernetes to give us the unstructured object and then give it a JSON and it marshals it in and then we can deal with that. So that's basically why.
Yeah, I'll give a shorter answer. Doing DuckTyping like this is, I think, slightly harder than just having fixed types everywhere. Taking it the next level and having it be a bit more dynamic gets really, really hard. You know, it may be something interesting to explore, but I mean, where we are for some of the shapes we've had to reason about, same shape's been pretty effective, partly because of API consistency and the API principles in Kubernetes, right? So one of the duck types is status conditions have a pretty regular shape across Kubernetes resources. All of the apps resources did a really good job of consistency across that class.
There's some other like more practical examples where everyone tends to type the kind, but Kubernetes doesn't operate on the kind. It operates on the resource, which is pluralized. The pluralization operates on English, and that's broken, right? So to convert from kind to resource, you can actually go and query the CRDs or have a list or whatever. So that's kind of the first iteration of what started some of the polymorphic parts.
Okay, we have time for one short question and short answer. Anyone at the back?
Hope it's a quack. Quack.
When you're building controllers that are like doing this type of duck typing, do you have any thought towards actually being able to wire in like informers and things like that for the subtypes that they actually generate as well?
So we actually have duck typed informers.
Okay.
So we can you set it up slightly different. You have to give it a GBK so that you can actually make the correct
Right.
API call. But then the controller gets back the duct type thing, so it reduces a step for us.
Right. What I was thinking is like from that top level type, there are going to be other objects that are other types that are generated by the controller that's managing that other type, and you might also want to watch those like sub objects that they generate.
Sure. I think that's the next step.
Yeah.
Doing this, the preparation for this demo, we ran into a problem of, great, we understand some of the DAG in the data plane, but we start to need to understand the ownerships for that exact reason. We don't know what resource just wants to be deleted because a child was deleted, or if the deployment made a replica set.
Yeah.
Right.
So I think one of the interesting things in this example, so I think, correct me if I'm wrong, but we've got the CRD controller, and that CRD controller is going to stamp out the duck-typed controllers. So what you're talking about is effectively if those these instances down here, boo, bar, baz, if those are creating resources, basically having informers for those resources. Yeah. So I would expect that generally, whatever reconciliation process you're writing, you are maybe taking this sort of abstraction of the concrete types, that the boo, the bar, the baz, and you're reasoning about it in terms of, say, what images are there. And the types you're actually instantiating are likely concrete types. So before you even stamp out boo, bar, and baz, you can actually start up informers for those. And then as you stamp out the duck-typed controllers, they can basically leverage the existing shared informer that was started up and then just sort of pick up from that. Does that make sense? Okay.
I think
He said, yes, it made sense.
Okay. Thank you so much for joining, and Scott and Matt, round of applause.
Don't